This lesson is about the intensity of waves. And remember that waves transmit energy, but they don't transmit matter. And also remember from our discussions of simple harmonic oscillators that the total energy of a simple harmonic oscillator is proportional to its amplitude squared. For example, if we're talking about a mass on a spring, its total energy is equal to half times the spring constant times the amplitude squared. And the maximum kinetic energy is equal to that total energy because there is a point at the equilibrium position where the potential energy is zero. So all the energy is just kinetic. And if you want to think of a traveling wave as just a series of oscillators going up and down, then it makes sense that the energy of a traveling wave is also proportional to the square of its amplitude. So if you double the amplitude of a wave, you quadruple its energy. And a wave has energy because if you think about the last particle in it, it's able to do work on whatever comes next. Think of waves crashing on a shore, or think about sound waves making your eardrum vibrate. They carry energy. So let's introduce now a new concept called intensity. Intensity is defined as power per unit area. And intensity is important because it's related to how we perceive waves. It's related to how we perceive the loudness of sound waves or the brightness of light. So power, recall, is energy divided by time and has units watts. So the units of intensity would be watts per meter squared. Watts from the power, meter squared from the area. And this is basically saying how much power you are intercepting with your detector. So if you imagine your ear and you've got sound waves moving towards it, we want to know the power per unit area because we're only intercepting the energy over a particular area. Now, for a wave on a string, if we assume that there's no damping, distance makes no difference because the amplitude doesn't change, the energy doesn't change. But when we have a wave spreading out in 3 dimensions, as you move away from the source, the same energy is getting spread out over a larger area. Let me give a diagram to show what I mean. In the center here we have a source, and that source is radiating energy in all directions. And these 2 circles represent 3-dimensional spheres that are like shells where I'm collecting the energy around this source. And if I were somehow able to collect up all the energy at the surface of this sphere and all the energy at the surface of this sphere, assuming the inner sphere in that case was transparent, I would get exactly the same total because the energy has nowhere else to go but out. And I could go to larger and larger spheres and I'd always find the same total energy spread across that whole surface area of the sphere as I did on any inner ones. So we now need to think about what's going on per unit area. We've reasoned out that we're getting less energy per unit area as we go out, but let's actually quantify that. We know that the area of a sphere is equal to 4 pi r squared, where r is the radius. So let's go out to the surface of this sphere. So if I imagine the energy radiating outwards, we could take a look at a piece of this surface area that I'm going to shade in like that. And we'll call that intensity 1. So the intensity 1 is going to be equal to the power of the source. And of course, remember that the power of the source itself is going to be proportional to the amplitude squared at the source. So the power of the source divided by, I'm going to call this R1 squared. So this distance here is R1. So we can see that the intensity then is proportional to 1 over r squared, where r is the radius of the sphere, or equivalently, it's the distance from the source to the detector that we're using. And if we were to carry this on further out here and look at a piece of the surface area on the larger sphere, we'd get the same kind of thing. And here you can see that the same energy is being spread over this larger piece of surface area compared to this one. So if we were to go outwards, let's call this R2, and let's say that R2 is equal to twice R1, then the intensity at 2 would be the power of the source divided by 4 times pi times R2 squared, and we would see that the intensity, as we've doubled the distance, has been quartered because of this inverse square. And so here's another example of an inverse square law. We've seen one already with Newton's law of gravitation, and we'll see one again with Coulomb's law for the force between 2 charged particles. So in summary then, because the power of the source is in the numerator here, and the power of the source is proportional to the amplitude squared, the intensity of a wave is going to be directly proportional to its amplitude squared, and because the distance between the source and the detector is here in the denominator, and we have this inverse square relationship, the intensity of a wave is proportional to 1 over r squared, where r is the distance between the source and the detector. So that's an introduction to intensity of waves.